Okay, so thanks again for having me. I apologize, I'm going to be cutting right out after my talk because I had planned otherwise, and then my airline company changed my plans. So anyway, there were sort of three problems I wanted to mention. One is the improving the Moore bound. I hate to mention this because, like many problems just with graphs and eigenvalues, first of all, this may have nothing to do with eigenvalues, but it is a very difficult problem. It would be a great thing to get any improvement over this. So this is, I would say difficult, maybe very difficult. The other question would be to understand the spectral density of the non-backtracking matrix of a tree. And I haven't defined the non-backtracking matrix, so, but the tree that's uniform but not regular. And I honestly don't know how difficult this is or not. I suspect that these days you could take a computer, make simulations, and I don't know. Maybe difficult or not. And then the other question is there something other than the non-backtracking matrix that can be used to improve trace methods? So can you improve trace methods beyond the improvement that you get when you start with the adjacency matrix and make your way over to the non-backtracking matrix? So this is sort of, and we'll see how far we get. And we'll get only so far, and that's okay too. So I should at least tell people about the non-backtracking matrix, although a lot of people have seen this for various reasons. So if you have a graph, say with vertices and edges, let's take maybe a simple example. So we have two vertices. Now let's put in, let's make it a 3-edge graph. So these are self loops. So the non-backtracking matrix is indexed on directed edges. So the first step is, you think of this as really a graph on 6 directed edges. So you put in an edge, let's call this U and V. So you'll put an edge this way, an edge that way. And for this loop that locally looks like degree 2, you'll put in an edge this way and an edge the other way. And we'll call this, we'll think of directed edges. So we'll say if this is the directed edge E1, this will be the inverse edge. And if this is the edge E2, this will be the inverse edge. And if this is E3, then this will be E3 inverse. So you think of it this way. So now, this is really a graph with vertices UV, and you have directed edges. E1 plus or minus, E2 plus or minus, E3 plus or minus. And then the non-backtracking matrix is indexed on the directed edges. So PG is indexed on the directed edges of the graph. And the rule is that you say that E is connected to F as directed edges if there's a walk from E that starts in E and continues on in F, and it doesn't immediately backtrack. So in the example here, maybe I won't do all of it, but the non-backtracking matrix. So it's some 6 by 6 matrix. You have E1, E1 inverse, E2, E2 inverse, E3, E3 inverse, E1, E1 inverse, E2, E2 inverse, E3, E3 inverse. And then if you go from E1 and you continue on E1, that's a non-backtracking walk because you're not backtracking. Whereas if you go E1 and then E1 inverse, it backtracks. So here, you're allowed to go from E1 to E1, but not to E1 inverse. You can go from E1 to E2, because that is a walk. But all the other edges start at another vertex, so they're not even a walk. And so on. So any questions on the non-backtracking matrix? That's right, that's right. So if I had like another self loop here, in fact, sometimes it's more interesting. The most interesting graph is the graph with one vertex. And in that case, you have single vertex. You have an E1, E1 inverse, E2, E2 inverse. And then you can go from E1 to E1, but not E1 inverse, E1, E2, or E1 to E2 inverse. In fact, well, that's a good, let's write that one down. So it's E1, E1 inverse, E2, E2 inverse. E1, E1 inverse, E2, E2 inverse. So from E1, you can go to E1, but not to E1 inverse, but to the other two edges. And similarly, from the E2 or E2 inverse, you can go to E1, but you can follow yourself, but not the other edge. And let's just make a quick remark. If we look at the eigenvalues, so if let's say I'll use mu1 of G, so I'll denote the eigenvalues of the non-backtracking matrix by mu. The adjacency matrix, I use lambdas to denote the eigenvalues. Here, the adjacency matrix is a 1-by-1 matrix with a 4 in it. Adjacency matrix is a 4. Here are the eigenvalues. So the row sums are 3, so 3 is certainly in there. And it's the largest one. It's the Frobenius eigenvalue. And then the other ones turn out to be a 1 and a 1 and a -1. So it turns out the eigen data of the adjacency matrix, certainly the eigenvalue, is equivalent to the eigenvalue of non-backtracking matrix. And this is typically called the Ihara formula. Ihara Hashimoto, Ihara Tsunada. Basically, Ihara was working with p-adic groups, writing down zeta functions. And then at some point, they say it was Serre who pointed out that he's actually doing graph theory without knowing it. And Hashimoto, his student, and Tsunada also realized graph theory. And what we call the Ihara formula, or maybe Ihara mental formula gives a recipe for going between the eigenvalues of the V by V matrix and the E directed by E directed matrix. And the formula says that if you want to look at the eigenvalues, call them mu of the non-backtracking matrix, they come in basically two flavors. So I just mentioned this identity is on the directed edges. So the first thing is that there's always plus and minus one. And the power is whatever it needs to be, which turns out to be the negative Euler characteristic of the graph. But, this is really kind of, whatever's needed. The real interesting part comes from the adjacency matrix. And for each eigenvalue, I mean, the formula is mu squared minus mu times the adjacency matrix. Here's the trouble. If it's a regular graph, it's a multiple of the identity matrix. If not, it isn't. So this is plus the degree counting diagonal matrix minus one. So d sub g is the degree of the first vertex, degree of the second vertex, and so on. Sometimes d sub g minus one is called q for a reason that number theorists will tell you. This is some maybe form of the Poisson summation formula or the Selberg trace formula, because what the trace of the non-backtracking matrix is, it's the number of walks that start somewhere and end up just before starting this. So and this is what we use for trace methods. So if you take the trace of the adjacency matrix to the kth power, what you get are just the number of walks of length k. Well, let me say more generally. The trace, if you take the kth power of the adjacency matrix and you look at the walks from the UV entry, this is the number of walks of length k from U to V. If you look at the non-backtracking matrix and you start with E1, which is a directed edge, I'll just put the little hat to remind you it's directed. This counts the number of ways which you can start at E1 and then go in some non-backtracking fashion and arrive at E2. So this is number of non-backtracking walks. Of length k from E1 to E2. So the trace in particular, a walk in the graph from U to V, looks like you start at U, you go some kind of walk to V, and if you look at a walk from U to U, you're just kind of walking along and coming back to U. So the trace of the non-backtracking matrix to the K is just the sum of the number of walks from any vertex to itself is therefore the number of closed walks of length K. in the graph. You start here, and you wind up back at some vertex. The trace of the non-backtracking matrix means that you start at an edge E1, you go to an edge E2, E3, in some non-backtracking fashion, and you wind up back at E sub 1. So it's the number of non-backtracking walks that close up at an edge in a non-backtracking way. So it's you can call this a number of things, but you might call this the number of either strictly closed non-backtracking walks, cyclically closed. In geometry, these are called closed geodesics. Or in graph theory, you might call them, strictly non-backtracking closed. There's a number of names you can use. So let me leave this example on. Let's see. So what does this mean? It means that if it's deregular, then this is an identity matrix. And so the determinant of this, you can solve eigenvalue for eigenvalue. If these things don't commute, you're in a whole bunch of trouble. But the tamest case is where they commute. So let's say that dg is just d times the identity. In other words, the graph is deregular. So that from every vertex, you have d edges coming out. In that case, what this says is that so you get a bunch of eigenvalues that are plus or minus 1. And the real interesting part is that for every eigenvalue lambda, you solve this equation and you get 2 eigenvalues. So for, so the eigenvalues of the non-backtracking matrix, you get a bunch of plus and minus 1s with whatever multiplicity you need to have. And then if you have an eigenvalue lambda I of the adjacency matrix, what you do is you solve the quadratic equation mu squared minus mu lambda I plus d minus 1 is equal to 0. And you get 2 eigenvalues there. Anyway, this is a picture you really ought to draw carefully to understand this. In particular, for the eigenvalue d, for the first eigenvalue, which is d in a deregular matrix, you're solving, mu squared minus mu d plus d minus 1 equals 0, and you get that the 2 eigenvalues are, what should the first one be? Without solving the quadratic equation, morally, what should the first one be? The d in the adjacency matrix is just the fact you have d edges. Pardon? It's even simpler than that. Okay, yeah, okay. You can plug in 1. That's the one I didn't want to get, but okay, plug in 1. You got 1. 1 is an eigenvalue. What's the other one then? If their product is d minus 1. D minus 1. And that sort of morally comes from the d, because that's what, that's how the walks are occurring. So in a deregular graph, you have d edges. On the non-backtracking matrix, it means that for each edge, you have d minus 1 ways of continuing in a non-backtracking fashion. And this is sort of the thing that tells you, the d tells you what's the big thing, and the d minus 1 tells you what's the largest Cohen-Frobenius eigenvalue there. Okay. So now we draw a picture. Of course, just to take this one further, well, okay, so let's draw a picture. So mu squared minus mu lambda plus d minus 1 is equal to 0. Do this like, give you nightmares of high school math, which means grinding away formulas, mu is, whatever that one is, maybe it's lambda, I forget. But I do remember plus or minus b squared minus 4ac. Mu squared minus 4 minus 1. Yeah, right. Thanks. Well, this is complex precisely when you're in the 2 squared of d minus 1 range. So if lambda in absolute value is less than or equal to 4d minus 1 square root, which happens to be 2 squared of d minus 1, which should look familiar from yesterday, you get a complex root, 2 complex roots. And the 2 complex roots are of absolute value d minus 1. So without going over the whole analysis of this quadratic equation, what this means is the following. So the eigenvalues are somewhere between d and minus d, and there is this special range of interest where they mostly occur, just from the Keston-McKay law, which is minus 2 squared of d minus 1 and 2 squared of d minus 1. And what this is telling you is that if you look at the corresponding eigenvalues mu, so of course it's not a symmetric matrix, you get complex eigenvalues, but what you do have is you have circle of radius square root of d minus 1. Try to push my luck on the colors here. So if you're within this range, what you get are 2 eigenvalues kind of around here. If you're at d, then you've got an eigenvalue at d minus 1 and an eigenvalue at 1. So in other words, a Ramanujan graph, meaning that all eigenvalues are within the plus or minus 2 squared d minus 1 range, means that all of those are on the unit circle. And then you've got one here. So just like for the adjacency matrix, you'll either have real eigenvalues somewhere along this line, a whole bunch of them at 1 and minus 1 when the graph is big, but the essential ones that are interesting, either take each value within the sort of plus or minus d minus 1 range to 2 eigenvalues here. Otherwise, you have 2 eigenvalues whose product is d minus 1. When the graph isn't regular, everything goes out the window because the matrices don't commute. And so if you try to solve, this quadratic equation, this is not the identity matrix. And it turns out that the spectrum of such things tends to look two-dimensional. Okay, any questions? Okay, so let me, in 3 minutes, talk about the Moore bound. Maybe I should spend a minute and a half, or wave my hands for a minute and a half, and then 45 seconds tell you, because it's a difficult question. So here's a question. Given N and D, what is the largest possible girth of a graph on N vertices and D regular? The girth is just the length of the shortest cycle. In other words, to link to Ahmed's talk yesterday, it's kind of how far the thing looks like a tree locally. So the girth is length of the shortest cycle in other words, that's essentially the same thing as saying you take every single vertex, you start growing a tree, and roughly at the girth divided by 2, you get a complete tree. And then it could be right at the end, maybe this vertex, A is the same as this vertex A, when you go just a little bit farther, meaning that you have a non-backtracking walk from A to A, which is a cycle. Okay. I will talk more than a minute about this, but yeah. I like, I think it's Semeredy who has the notion of illegal thinking, which is, what do you do when you really just kind of want to mess around and dream and try stuff on a difficult problem? This is one of my illegal thinking problems. I know, politically, I shouldn't be spending a lot of time on it. Chances are it's one of these high-risk things. The older you get, however, the less you need to publish, profusely. So maybe do a little bit more of this, more thinking on the Moore bound. Anyway, the bound there's a trivial bound, which is if you start growing a tree, it's D regular. So this is degree D. Everyone here has degree D minus 1. Then once you fill up all the vertices, there has to be 2 that are the same. So if you look at this as level 1, or maybe this is level 0, level 1. So you've got, 1 vertex at level 0. At level 1, you've got D vertices. At the next level here, if this is a perfect tree, you get D minus 1. And then D minus 1 squared, and so on. If all of these are distinct vertices, fine. But at the point where this is larger than n, 2 of the vertices have to be the same. And therefore, you have a cycle of length 2 of this, whatever this level is. So you get to level k, and let's say that you're at level k. So you get D times D minus 1 to the k. If this is strictly bigger than n, then you have a cycle. of length. You have to have a cycle of length 2k. This is said to have appeared at, I think, maybe an IBM journal or AT&T journal sometime in the 50s by Moore. Maybe not even publicly available. It's called the Moore bound. This is kind of the first thing that you notice. This bound, so what is this bound? Give you this means that the girth has to be no larger than 2k when k is the value at which this happened, roughly speaking. Now you can kind of, the rest of this is geometrically decreasing in that, but roughly, so at k, which is roughly log d minus 1 of n, you get this inequality holds, and so the girth is roughly less than 2 log d minus 1 of n. Since the 50s or whenever this was noticed, no one has improved this by more than an additive constant, like subtracting 1 or 2 off of this, and not very small than this bound. If you take the Lubotsky, Phillips-Sarnak, Margulis expanders, you can get a girth that's as large as 4/3 log d minus 1 of n. And it's an old theorem of Erdős and Sachs that for any, you can just always build a graph for any d and n where the girth is at least roughly 1 times log base d minus 1 of n. These ones are only for certain values of d and n, namely d has to be 1 plus a prime power, n a certain prime, I think congruent to 3 modulo 4. It's actually the bipartite LPS graph that gives you a large girth, not the non-bipartite, which is really the good expander. See, I'm spending more time on this than I planned. Okay, this is a fun thing. So there's a paper by Amit Puri Lineal from 2002, which says that with spectral methods on the adjacency matrix, you can precisely reproduce, using the fact that the eigenvalues of a graph are something between d and minus d, you can exactly reproduce this bound. But you would have to do it for a continuous distribution. And so there's a nice quote about Alice having seen a cat without a smile, but never seen a smile without a cat. So if this makes sense. So, there's a continuous thing that does this exactly. But of course, graphs have certain restrictions. In particular, the eigenvalues are not a continuous distribution. They're, just n points somewhere in here. So this, you can exactly recover the Moore bound. Via it's a fairly elaborate calculation using the moment method, things you know about A sub G. Let's this is kind of, maybe I'll just spend the whole 15 minutes on this. So what about, let's look at the trace of V sub G to the K and say that K is even. Well, if K is even, and really you have two choices, either you have real eigenvalues or complex ones, and there's only roughly n of these, what do you get? I mean, it's got to be at least d minus 1 to the k. And then something positive, for all the real mu's. And then what's left? Well, you have 2n minus 2 that are complex on the circle if you're not real, floating somewhere here. And conceivably, if things are really bad for you, they could all be in this power right at this edge. So it could be as bad as d minus 1 to the k over 2. And if they all conspired against you to make things as small as possible, you get a minus 1. It's bigger than d minus 1 to the k. Plus, let's be generous and call this 2n times d minus 1 to the k over 2. And if things were really as bad as they can be, you get a minus here. And, this is bigger than 0 if d minus k is bigger than 2n d minus 1 to the k over 2. So this is an immediate proof using the Hara formula and the non-backtracking eigenvalues that for any graph, the girth has to be not exactly the Moore bound, but very close to it without doing anything. This is one piece of evidence for me that working with a non-backtracking matrix does better things. It depends who you ask. I think Nati Lineal is really like a big enthusiast of this problem. So am I. And I think when we were working together on this, we were hoping to shave this down by a 1.99999 or something. It's doing a whole bunch of calculations, some ideas we discussed, long calculation, bigger than 2. Long calculation, big sphere packing, this, bigger than 2. So at some point, it was believed that there was maybe a something like 7/4 construction, but that didn't hold, and people have tried. And I don't think that for a general n and d, let's say n is not 1 plus a prime or the order of SL2Q, nobody knows. Yeah. So the LPS graphs and Margulis are Cayley graphs. The only other method that I know is Erdős and Sachs that will build one, vertex by vertex to attain this bound. Erdős Sachs, no. They're just saying, up to a certain n, we have this. We're going to add one more vertex, and if the girth is less than this, we're going to make it bigger. Some vertex you add, it creates a cycle that you don't like, and you switch things around. It's constructive in the sense that if you are happy to construct these in polynomial time, then yes, it is. I think everything they do, I'm not entirely sure, but I think what they're looking for, yeah, because they're looking for stuff only up to this depth, so it should be. And here I've talked a lot about this problem. Okay. Any questions about this? This is not what you should be working on, by the way, especially if you are young and you don't have tenure yet and you don't have your full professor yet. You should not really be spending a lot of time on this. But Yeah. Yeah, the thing is, the Custon-McKay law is going to tell you that actually you will get stuff with a lot of minus ones. I mean, in a sense, you have to be pretty close to -1 here, at least when you average the real part. It has to be very close to -1, because otherwise this would be positive and you get a cycle. So yeah, yeah, yeah. Yeah, if you could find some like interesting non-trivial invariant, maybe you could say this can't happen. And no one's been able to do better than 4/3 of this. So there's a constant, there's a gap in the constant factor.